The content in this presentation aligns with pages 80 through 84 of your textbook, and it's meant to help you achieve Learning Objective 17, which is to summarize several applications of temperature data. So how do we use temperature data? If you haven't already done this, it's a good idea to skim those pages, 80 through 84, before you watch the rest of the video, focusing as usual on the bold words, the figures, and their captions. Please plan to read the content thoroughly before you attempt the quizzes. There are many useful and practical applications for temperature data. In this section of the presentation, you'll learn about some simple but important indexes that relate to energy use, agriculture, and human comfort. 3 indexes of temperature have the term degree days as part of their name. So those are heating degree days, cooling degree days, and growing degree days. The first 2 are relative measures that allow us to evaluate the weather-produced needs and costs of heating and cooling. And that's a big part of economic decisions made about when to stockpile fuel, what the rate of fuel, what the cost should be to the consumer. So economics are a big part of this. Another one, though, is basic industry, used mostly by the agricultural community to estimate when the crops that they're growing will be mature. Heating degree days they're a commonly used method for evaluating energy demand and consumption. This index starts from the assumption that heating is not required in a building when the daily mean temperature outdoors is 65 degrees or higher. And that's Fahrenheit degrees. Because the National Weather Service and the U.S. News media still compute and report degree day information in Fahrenheit, we keep using that Fahrenheit scale throughout this discussion. Simply, each degree of temperature below 65 degrees is counted as 1 heating degree day. So therefore, heating degree days are determined each day by subtracting the daily mean below 65 from 65. So a day with a mean temperature of 50 has 15 heating degree days because 65 minus 50 is 15. One with an average temperature of 65 would have none. So the amount of heat required to maintain a certain temperature in a building is proportional to the total heating degree days. This linear relationship means that doubling the heating degree days usually doubles the fuel consumption. So a fuel bill is generally twice as high for a month with 1,000 heating degree days as it is for a month with 500. When seasonal totals are compared for different places, we can estimate differences in seasonal fuel consumption. For example, more than 5 times as much fuel is required to heat a building in Chicago. That's in this zone of the country where we see 6,500 or so total heating degree days. Then it would cost to heat a similar building in Los Angeles, which is down here and in the 1,700 degree heating days. This statement's true, however, only if we assume that building construction and living habitats in those areas are the same. So each day, the previous day's accumulation is reported along with the total thus far in the season. So for reporting purposes, the heating season is defined as the period from July 1st through June 30th. So that's sort of a heating year. Those reports often include a comparison with the total up to this date last year or with the long-term average for this date. So it's a relatively simple matter to judge whether the season thus far is above, below, or near normal. Just as fuel needs for heating can be estimated and compared by using heating degree days, the amount of power required to cool a building can be estimated using a similar index called cooling degree days. Because the 65 degree Fahrenheit base temperature is also used in calculating that index, cooling degree days are determined each day by subtracting 65 from the daily mean. So if the mean temperature for a given day is 80 degrees, you have 15 cooling degree days. Mean annual totals of cooling degree days for selected cities are shown on this map. By comparing the totals for, say, Baltimore and Miami, you can see, let me show you, Baltimore is right in there. And Miami, let's look at Florida down here, is in the 3,500 range, and Baltimore closer to 1,200 maybe. You can see that fuel requirements for cooling degree days, you use them just the same way as you would with heating degree days. Because the 65 degree base temperature is used, then we can compare those two cities. The cooling season is conventionally measured from January 1st through December 31st. So we start at a point when we assume nobody's using their air conditioner, right? The whole year. That's a standard year. So when cooling degree day totals are reported, the number represents the accumulation since January 1st of that year. Although indices that are more sophisticated than heating and cooling degree days have been proposed to take into account the effects of wind speed and solar radiation and humidity, they still kind of use the degree days most of all those indexes. A third degree day is the growing degree day. And it's another practical application of the temperature data used in agriculture to determine the approximate date when crops will be ready to harvest. So this index is called the growing degree day. It's the number of growing degree days for a particular crop on any day is the difference between the daily mean temperature and the base temperature of the crop, which is the minimum temperature required for it to grow. For example, the base temperature for sweet corn is 50 degrees, and for peas, it's 40 degrees. Thus, on a day when the mean temperature is 75 degrees, the number of growing degree days for sweet corn is 25, and the number for peas is 35. Starting with the onset of the growth season, the daily growing degree day values are added. So if 2,000 growing degree days are needed for a crop to mature, it should be ready to harvest when the accumulation reaches 2,000. Although many factors important to plant growth are not included in the index, like moisture conditions and sunlight, the system still serves a simple, widely used tool in determining the approximate dates of crop maturity. So these are not degree days. These next two are indexes for human discomfort. Summertime weather reports often try to make people aware of potential harmful effects of high humidity coupled with high temperatures. And in the winter, we get reminded about the effect of strong winds combined with low temperatures. In the first instance, we're cautioned about heat stress and the possibility of heat stroke. And in the second case, we're warned about wind chill and the potential dangers of frostbite. These indexes are expressions of apparent temperature, and that's the temperature that you feel. Heat stress and wind chill are based on the fact that our sensation of temperature is often different from the actual air temperature recorded by a thermometer. So the human body is a heat generator that continually releases energy. Anything that influences the rate of heat loss from the body also influences our sensation of temperature, thereby affecting our feeling of comfort. Several factors control the thermal comfort of the human body, and certainly air temperature is a major one. But other conditions are also significant, like relative humidity, the wind, and the amount of sunshine. High humidity contributes significantly to the discomfort people feel during a heat wave. Why, for example, are hot and muggy days so uncomfortable? Humans, like all mammals, are warm-blooded creatures who maintain constant body temperature regardless of the temperature of the environment. One of the ways the body prevents overheating is by perspiring. However, this process does little to cool the body unless that perspiration can evaporate. So it's the cooling created by the evaporation of perspiration that reduces your body temperature. Because high humidities retard or prevent evaporation, people are more uncomfortable on a hot and humid day than they are on a hot and dry day. Generally, temperature and humidity are the most important elements influencing summertime human comfort. One index widely used by the National Weather Service that combines those factors to establish a degree of comfort or discomfort is called the heat stress index, or simply the heat index. In this figure, you can see that as relative humidity increases, the apparent temperature and heat stress increases as well. Further, when the relative humidity is low, the apparent temperature can have a value that's less than the actual air temperature. It's important to note that factors such as the length of exposure to direct sunlight, the wind speed, and the general health of the individual greatly affect the amount of stress a person will experience. In addition, while a period of hot, humid weather in New Orleans might be reasonably well tolerated by its residents, a similar event in a northern city such as Minneapolis would not be well tolerated. This occurs because hot and humid weather is more taxing on people who live where those conditions are relatively rare than it is on people who live where prolonged periods of heat and high humidity are the rule. Most everyone is familiar with the wintertime cooling power of moving air. When the wind blows on a cold day, we realize quickly that comfort would improve if the wind would stop. A stiff breeze will penetrate ordinary clothing and reduce its capacity to retain body heat while causing exposed parts of the body to chill rapidly. Not only is cooling by evaporation heightened in this situation, but the wind is also acting to carry that heat away from the body by constantly replacing warmer air next to the body with colder air. The National Weather Service uses the wind chill temperature index, and that's designed to calculate how the wind and cold feel on human skin. The index accounts for wind effects at face level and takes into account body heat loss estimates. It was tested on human subjects in a chilled wind tunnel. The results of those trials were used to validate and improve the accuracy of the formula. The wind chill chart includes a frostbite indicator that shows where temperature, wind speed, and exposure time produce frostbite. It's worth pointing out that in contrast to a cold and windy day, a calm and sunny day in winter feels warmer than the thermometer reading. In this situation, the warm feeling is caused by the absorption of direct solar radiation by the body. The index does not take into account any offset effect of solar radiation on wind chill. Such factor may be added in the future, but it's important to remember that the wind chill temperature is only an estimate of human discomfort. The degree of discomfort felt by different people varies because it's influenced by other factors. So even if clothing is assumed to be the same, individuals vary widely in their responses because of such factors as age or physical condition, state of health, or level of activity. Nevertheless, as a relative measure, the wind chill temperature index is useful because it allows people to make more informed judgments regarding the potential harmful effects of wind and cold. So use the content provided here and on the Canvas site, as well as the outside sources like the internet and your textbook, to verify that you can answer these questions. If you can comfortably answer these questions, you're in great shape. If you can't, review the textbook, rewatch the video, and see if those abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.